All right, thanks, Mark. Thanks for joining us. I'm going to talk about what's going to be available for liquid interface science program at ChemMatCARS after APS upgrade. And some information could be already well known for some audience today, but if that's the case, please bear with me, okay? And this is our sector layout. You have seen that a couple of times already early this hour. We're going to have two beam lines, 15ID1 and 15ID2. And for liquid interface, we're going to have two end stations as highlighted here. Station C at ID1 line, station E at ID2 line. And I know Mark already introduced the beamline scientist for this program, but I feel like, it's still my duty to do that. And I've been on this program quite long, like 10 years already. And I also introduced these two new beamline scientists we hired during the shutdown, Dan and Dave. And since they joined us, actually they already made a number of contributions, and I'm going to highlight a couple of them during my talk. Well, we have two beamlines. Two beamlines have different features. They have, Yushan already mentioned that. They have different energy range. They also have different optics in our front-end optical enclosure. And based on these different features, we have our preference of doing like what kind of experiment at which beamline. And for example, for station C at ID1 line, which is going to be available at 2026, in this station, we're going to have high flux at high energy range, which is very important for liquid-liquid interface study. So that's why we want to do the liquid-liquid in this station. And also, Mark mentioned we're going to have a mechanical focusing mirror in this beam line. So that's going to provide a fixed beam size within a wide X-ray range, which is critical for the X-ray spectroscopy measurement, at least for the experiment we're interested in. For the station E, which is going to be available later 2026, we're going to implement a new scattering instrument. It's a double crystal diffractometer, which is optimized for the solid liquid scattering geometry. And that's why I want to put a solid liquid experiment in this station. And the same thing on this station, we're going to have longer sample to detect distance, which is always something good to have for the G-STACS measurement. Oh, in this talk, I mainly will focus on what's going to be available for C station because it's going to come up early. And towards the end of this talk, I'm probably going to spend a couple of slides on the E station as well. Okay, I'm going to start with technical capabilities in the C station. And as many of you know, X-ray scattering truly is the leading technique to study structure at a liquid interface with very high spatial resolution. For example, we can measure electron density profile on a sub-nanometer scale. And from this electron density profile, we can determine the molecular structure normal to the interface, which could be ordered or disordered as shown here. The technique we have include X-ray reflectivity, which is a traditional technique. We also can do the JIXAs, which is a faster version of X-ray reflectivity and usually good for the dynamic system. We can also measure in-plane ordering, and for example, particles, molecules, they can form in-plane long-range ordering at the liquid interface, and we can measure this ordering with the sub-Angstrom resolution. And available techniques include like GIXD, which is good for smaller size particles like ions and lipids, and GSAX, GWAX are good for the large size particles. We also have time resolved technique, this called 2D GID measurement, which can monitor the structural evolution on the time scale at the order of like minute, even tens of seconds. Other than in-plane and out-plane structure, we also can directly measure the specific element at interface. For example, we can measure this interfacial coverage of metal ions, as well as their chemical environment, like hydrogen shell at the interface. The technique we have for this part include XFNTR, this X-ray fluorescence near total reflection. And the other one we have is X-ray absorption spectroscopy, which I'm going to expand a little bit more on the next slide. Well, this is one of the recent development actually happened right before the APS upgrade. This XR measurement at the liquid interface. It measures bonding configurations and oxidation state of target ions at a liquid interface, which many believe is different from the bulk, but generally remains unknown. Here's the setup. The X-ray comes in from the left side, from right side, and goes through the BPM, is a beam position monitor, which locks beam to the fixed location during this within this energy range, which is typically about 800 eV. And right after that is a reflecting mirror, which deflects beam to the liquid surface with the desired angle, which is typically below the critical angle. So we're going to have an external total reflection. And on this condition, X-ray only penetrates the bulk on the order of nanometers, which give you a surface selectivity. And we place this energy dispositive detector on top of the sample to connect the fluorescence signal. The system we studied is a mixture of a peptide and rare earth element mixture in the water, and they bind to each other in the bulk and form this small layer at the water surface. The result shows that there's only one coordination shell, and within that coordination shell, there are like 8 oxygen atoms, and that kind of information you can get from this technique. During the shutdown, we also implement a couple of new hardware to enhance this technique. One thing we did is get a longer reflector mirror. We increased the size from 10 centimeter to 30 centimeter, which allows go to high energy, so we can explore the KH of heavy element. The another addition is this 7-element silicon drift detector, as well as this advanced readout device, Express MIDI Express 3. The combination of these two, it's going to it's going to help us to improve the data connection efficiency quite a lot. Okay, now let's jump to the hardware availability. The picture here provides a wide angle view of our C station. It's right in the middle is our scattering instrument. It's a unique instrument. There are only 2 of them like this in the entire US, and with the other one at NSLS2. I think Ben, Oko, and Honghu, they're beamline scientists on that station. I think they're in the audience today as well. In this station, we have a full tunable X-ray range from 6 to 70 keV, which is widest worldwide for liquid interface facilities. And we have high flux and high energy range, which making us as one of the best places to study liquid-liquid interface. And also tunable energy allow us to do this kind of absorption measurement. Well, after APS upgrade with the new APS X-ray source and our new optics, our beam size is going to be significantly improved. For example, with the mirror focusing, our beam size is going to be, our vertical beam size is going to be improved by almost order of magnitude, which allows to study the sample coming with an even smaller sample size. On the right side, I'm showing a connection of our area detectors. This area detectors not only in general improved our data connection efficiency, but also has been a key for some technical development, such as this time result techniques I just mentioned like a few slides back. For sample environments, we do provide some in-house sample environments. Many of you in the audience are already familiar with them. For the liquid vapor interface, we use standard non-meter trough environment, which has a high compression ratio and wide temperature control range. A single barrier is used to control molecules on the liquid interface. The whole setup is compatible with different type of inserts, large or small, as shown here on the top right corner. The small inserts are available for expensive material. For the liquid interface sample cell, the setup is a little bit more complicated, but we do have special sample cell for the general users. Particularly for this one, we do have oil on the top face and water at the bottom face. On software side, we have developed a couple of software packages, data processing software, LSS Reader, and the other one is data analysis software, XModel Fit. Many of you are already very familiar with these 2 software. And both of them are Python-based, have graphic user interface. Again, you can see here from these 2 movies, and they're easy to use. And also they're available for download on our GitHub account. And with these 2 software package, our users are able to view the data and analyze data in the real time. And we are the only liquid interface facility worldwide to provide such a complete data analysis software. And the development really had a huge impact on us, and numbers shows our community is really expanding. Well, here on this slide, I'd like to introduce our recent software development, feeding a biomembrane reflectivity, which is done by one of our new hire, Dan. Well, when it's come to the protein membrane interaction, we want to know more than just like a slab model, right? We want to know some more detailed structure information, such as the orientation of the protein, how deep the protein insert to the membrane layer, as well as area coverage. So for this kind of question, the traditional slab model won't work well. And a model of using this information directly as a feeding parameter actually has been established back to like 10 years ago by a couple of user groups, Max Schlossman group and K. Ellis group. but it was originally written in C and MATLAB. After joining us, Dan incorporated this model into the X model fit, and one of the advantages of doing this is to use this MCMC function within the optimal fit to establish the confidence interval of these fitting parameters. He also improved the algorithm. Now we can fit the data within a couple of seconds. All right, now let's shift to the station 2, which is going to be available later 2026. The new instrument we're implementing is this hybrid interface carrying instrument with the capability of studying sample orient either vertically or horizontally. It will be the first one in US. This instrument is optimized to study the liquid-liquid interface. That's why one of our new initiative in this station is to study the support bilayer, lipid bilayers. Okay, we moved ahead even without station, without instrument. We moved ahead with the flow cell design. This flow cell is compatible with a couple of lipid bilayer deposition methods and vesicle deposition and solvent exchange. A prototype cell has been already tested at the SPS beamline during the summer. All right, another development we're doing right now is a non-mere trough environment. Dave, another new beamline scientist, is actually currently working on this design. As this movie just showed, with this hinged enclosure design, it's going to be easier for our user to see and manipulate their samples. We also expect to have better temperature control and fast helium exchange. Well, the design is still ongoing, so if you have any suggestions, please contact Dave. Okay, this is my summary slide, that shows the estimate timeline for the availability of the techniques. I just mentioned that. And in different stations, for example, for C station, most technique will be available in early 2026. Other than this, with the exception of this absorption spectroscopy, which will come a little bit late since we need to use X-ray to do the commissioning for the new hardware we just got. For station E, some of these traditional techniques like reflectivity and GID will be available in late 2026, and others will be available early 2027. Okay, I'm going to stop here.